Let's take an example, just to get you into this analysis. So you have, in this case, a bivariate situation. You have two variable mathematics scores in grade 7 and grade 10. And for some people, you have missing data in grade 10. Perhaps they dropped out of high school and weren't there, or some other reason. Say that we assume bivariate normality for these two variables. Then Bayesian analysis considers three sets of unknowns: the two means, the two variances, and the covariance, where those two first bullets describe the 5 parameters of the bivariate normal, but we are going to break them up into the means and the variance covariance. But the third set are the missing values on Math 10 for the N2 people. So the missing values become unknowns in Bayes. They become parameters. You know, parameters are unknown things, but missing data pieces are unknown as well. So in your estimation, for the same price, you get estimates, you get the imputed values, so to speak. So the way this estimation goes is to use so-called Markov chain Monte Carlo techniques, which there are many different variations. Gibbs sampling, Metropolis Hastings, and many others are examples. Here's how it's done in Mplus. You start with drawing values for the two means. So first you try to figure out what the two means should be. Then, given the two means, you draw values for the N2 missing values on Math 10. And then given the means and the missing values, you draw values for the two variance covariance parameters. So 3 steps that you keep iterating. But first of all, what do I mean by draw? In ML, you don't draw anything. You move forward by looking for when the first order derivative gets to 0. And it just moves smoothly towards that. But in this case, the computations are based on random draws. So say that you have a random number generator that generates normal numbers. You take a random value. Often they're close to 0, but many are far off. That's what you do. You keep drawing. Very often in MCMC, the normal distribution that you draw from. You just draw a random value to get the two means. It's conditional distribution on the means, conditional on the other unknowns. And once you have those, you can draw values for the missing values. And once you have those, you can draw values for the variance covariance parameters. And then you go back to step 1, and step 2, and step 3, and magically this converges according to smart statisticians. And we keep doing this 100 times before we report the first iteration in the Mplus Tech 8 output, Technical 8 output. So it's random draws, and here's what it looks like when you draw. It's described in a trace plot. So on the x-axis we have the iterations, which eventually over there on the right somewhere converge. And I'm going to tell you what I mean by converge. On the y-axis we have one parameter, the mean for Math 10 that we're trying to estimate. So this is for one parameter. So we start at, say, a listwise estimate of the mean, 63.7, and then we take a random draw from the distribution, this distribution conditional on other unknown things, and it goes up a little bit, and then in the next iteration it goes down and down, down, and then up, down. And you see that it starts to come towards sort of a stable level here, but you have jumps up and down. What this eventually leads to is not a parameter estimate, not only a parameter estimate, it leads to a whole distribution for this parameter estimate. And how should you view the distribution? Well, you should really tilt your head to the left like this, and then see that if you imagine a distribution here, most values are in the middle, many are out in the tails. Can't you imagine a normal distribution there? Well, if you can't, we have a movie for you. We look at this posterior distribution, and here's what it looks like. I mean, rather the trace plot. And here are the parameter values, and we turn our head And this is what it looks like the other way, tilting to the left. And those points rumble down into a distribution. And we have now formed the posterior distribution of the parameter estimate. And we take that to be the estimate, the peak, or the median, or the mean. And we get the percentiles out of that posterior distribution. So the 95% credibility interval lies between here. That's it. That's how it should be viewed. So this becomes a distribution if we go far enough. We throw away an initial period of draws which are too far away from being stabilized around this mean. They are called the burn-in phase, and that's actually the first half of the distribution of the number of iterations. And we're going to work with two different processes like this going forward in parallel, computed on different processors, so it goes very quickly. And we take we throw away the first half for both of them. That means together they give the total number that you specified when you asked for the number of iterations. So what you end up with then after 10 iterations is something that doesn't look like much, but after 100 iterations you start discerning a normal distribution. After 500 it's getting even better, and 10,000 a very nicely smooth normal distribution for the mean under missing data. And the estimate then, just like ML that we talked about for missing data yesterday in the bivariate case, draws on all available data. It's a full information estimator, and it's unbiased and correct under MAR, missing at random, that is missingness that is predicted by variables that are observed that have no missing, namely the Math 7 score. And here's what it looks like. Bayesian posterior distribution. This is for the parameter estimate. In this case, it's actually the indirect effect of something in a mediation model. So you get the mean, the mean, the median, and the mode, and you can choose which one you like best. It usually doesn't make a difference. Some simulations say that the mean is better than the median, Mplus default is median, and you get the confidence bands here too. The percentiles, 2.5 percentile, 97.5. And we have a non-symmetric interval. That distance here is shorter than the distance up there, which it should be because of the skewedness there. And the point is that you would get almost exactly the same information if you did ML plus bootstrapping. This is the bootstrap parameter estimate distribution. So very often you're not going to find any difference between ML and Bayes. But in some cases, ML can't be used. Convergence, here's how you look at that. You look at the trace plot, in this case, using the default of 2 iterations going forward in parallel from different starting points. One is red and one is blue. Here's the cutoff where we throw away these draws, these iterations. Draw and iteration means the same thing. That's the burn-in period. And we use only these draws, these parameter value points, to form that posterior distribution by tilting our head to the left. So to judge convergence, there is a whole set of possibilities. And those who have used Bayes for many years, using, say, the BUGS program from Britain, you're familiar with the CODA program by Nicky Best and others, CODA. One criterion, but there are many others, is the potential scale reduction criterion, which is a PSR that's printed in technical 8 in Mplus, such that values close to 1 indicates convergence to a distribution that you can trust. And that means that the between-chain variation is small relative to the within-chain variation. You have within-chain variation, of course, because that's supposed to describe the full parameter distribution. But you don't want the between-chain variation to be large relative to the within-chain variation. Then you haven't gone to convergence yet. One big warning here, convergence needs to be, using PSR, needs to be taken very seriously. It could run into a problem called premature stoppage. So you have the PSR value on the y-axis, and you want to come down to the value 1, that line. X-axis is the iterations, MCMC, Markov chain Monte Carlo iterations. This PSR value can go down to 1 for several iterations, but then bounce up again until it stabilizes like that. So you want to make sure that if you have convergence, you may want to go a little further in the iterations so that you see values close to 1 for a longer time. It should be 1.0 something typically. 1.0, not 1.1. So that's something you should look out for. And where you look is, you ask for Tech 8 all the time in Bayes. It's very useful. That's why I recommended that to Ellen. So you have the iteration number here. It's numbered by the hundreds, like I mentioned. You have the PSR value here, and you get the parameter with the highest PSR here. So you see here, it starts already at very close to 1, but then eventually it goes up to 1.8, 1.2, and certainly it has not converged here. So you should continue until it stabilizes to have a lot of values in the 1.0 something range, a whole bunch of them. And you can see from the Tech 8 how long you have to go. In this case, perhaps you have to go to 5,000 iterations. And you see here the time that's needed for each iteration. So you can gauge from that in conjunction with how PSR behaves, you can judge how long the run is going to take. And some of them are going to take quite a long time. You need to look at trace plots that show the iterations over time. This is a good one. It's a level picture. It doesn't have an upwards or downwards trend, and you have nice zigzagging caterpillar behavior here. This is a bad plot. Even after throwing away these initial iterations, you have a progression that goes up and down, perhaps indicating 2 different solutions, and certainly not stabilizing. Likewise, you want to have a distribution of parameter estimate values where the draws are largely independent, so you can estimate the variance correctly, like independence in random sampling. And therefore, autocorrelation, that is correlation between values at different distance from each other in the iterations, the distance marked by this lag here goes from 1 to 30, those correlations should be very close to 0. And should not look like this, where the correlation is close to 1, even up to 30. That means that the parameter is very tough to estimate. The mixing is poor, mixing meaning that not only do we have correlated observations, but probably we don't visit all parts of the parameter space properly. You want to describe the parameter distribution very well. All right. That's the main guts of it. Speed of Bayesian Mplus, pretty good. Here's a paper that compared ML with Bayes for moderated mediation, a topic relevant to yesterday. And they used bugs, and Mplus was 15 times faster. And the reason is that Mplus uses Fortran. Mplus uses parallel computing, so each of those 2 chains are computed separately. And this bullet is due to Tiermer tailor-making every possible application area of Mplus. He tailor-makes how the Bayesian algorithm is written. It can be done in so many different ways, some very inefficient ways, and some very efficient ways. Largest updating blocks means that you work with, if unknowns like parameters and missing data are highly correlated, you want to put them in the same block, but you want to have uncorrelatedness between blocks. Tiermer is going to talk about that tomorrow morning. Now, I would also argue that Mplus Bayes is considerably easier to use than other Bayes programs, but you may have a different taste. I played around with bugs in the early 90s, and I found it quite technically oriented, statistically oriented towards the statistical PhD person rather than, say, psychologists who want to use advanced methodology and get some answers to their substantive questions. Nevertheless, even though Mplus Bayes is faster than other Bayes programs, it's going to take a lot longer doing DSEM modeling than the computing times that you're used to. So the talk that I'm going to give now on the applications of this, I'm going to use a data set with 230 people and about 150 time points. I do an n=1 analysis as a starting point. One person takes 0 seconds. So that's nice. But then I do a 2-level analysis, and we immediately jump up to 3, almost 4 minutes. And a cross-classified analysis, trying to find a trend, which I'm going to show is quite exciting how you can find a trend by cross-classified analysis. Takes a little bit over 1 minute. If you put the trend into the 2-level setting, it takes 4:42 instead of 3:54. If you could do a cross-classified trend analysis, it takes 34 minutes. Cross-classified factor analysis of ordinal indicators, in this case negative affect that we talked about this morning, almost an hour. If they're dichotomous or dichotomized, it's a little faster. If the indicators are continuous, it's even faster relative to the ordinal case. And this is the PC that I had 5 years ago. The most important thing is that I had 3.4 gigahertz for the processor. And now I just got a new computer that I haven't had time to unpack because of this workshop, which is going to cut off 33% of the time. It has 4.3 gigahertz. Yeah, but then you can also overclock it, which is the term for, souping it up a little bit. And then instead of dropping down by 33%, Morten tells me it's going to drop down to about 40% time saving. So that's pretty good. So that's 4.3 gigahertz, and overclocked is 4.8 gigahertz. So that's the most important for base. That's the gigahertz for the CPU is the most important factor. Yes, you should have more than one processor. I got 8 processors then. I think I have 8 processors now too. Having many more processors than 2 is more important for mixture modeling, where you do a lot of random starts searching around. But it's less important in this context. All right, if you want to read more about Bayes, and if you're statistically oriented, you should read this book. I recommend that. There are many others, of course. A more applied one is the Lynch book. We have lots of Bayes technical reports on the Mplus website under papers, Bayesian analysis, which documents very carefully everything we do. And that was written for version 6, so it goes back to 2010, I think. And that's the paper that I mentioned, where I played around with weakly informative priors for 2-level modeling. But if you really want to read about Bayes in the Mplus context, then you should read chapter 9 of this book that's floating around here, which is devoted to how Mplus does Bayes.